Okay, what we talked about yesterday is our change in kinetic energy equals our change in potential energy for a system, which is equal to our net work. Our work net is equal to force net times displacement. Our net force is equal to mass times acceleration. These are all things that we have gone through and continue to go through. And how else we find our force net is your force applied plus your force of friction plus all of our forces. Okay, so these are all things that we have dealt with this the last couple of days, and this back in our previous chapter. Force net is equal to mass times acceleration due to Newton's second law, Sir Fig of Isaac Newton. On a frozen pond, a person kicks a 10-kilogram sled, giving an initial speed of 2.5 meters per second. The coefficient of friction is 0.10. How far does the sled move before it stops? How far does it move before it stops? Well, we know we have an initial velocity at 2.5 meters per second. We have a mass, which is 10 kilograms. We have a coefficient of friction at 0.10. If we take an object and give it an initial push along the floor here, eventually the object stops. Why does it stop? Yes? Friction. Yeah, friction stops it. Okay, so friction will eventually stop something that you push unless you're in an entirely frictionless world, which we don't have. Which would be still cool to live in, but that's just me. So we have our force of friction that's going to eventually stop this. So friction will stop a sled. So if we have this, let's see, we have a sled here. We give it an initial velocity of 2.5 meters per second. We give it a shove. Eventually, it stops. We want to know how far does it travel before it stops. Well, we have these ideas over here. Change of kinetic energy is equal to change of potential energy equals our work net. We have work net is equal to force net times displacement. Force net is equal to mass times acceleration. And force net, I guess that we could throw in here, is the sum of the forces in a direction. whatever direction that is. Vertically, horizontally, whatever the sum of the forces is. When it stops, what's our final velocity, Lucas? 0. So we know final velocity is equal to 0 meters per second. Why? Because it stops. I have a mass. I have both velocities, initial and final velocity. What value can we find over there to the right? What value can we find? Well, what value deals with velocities, mass? What can we find? Riley? Find acceleration, we can find that. Yeah. But what else can we find over there to the right? Kinetic energy. Because we have an object in motion. So we have our change in kinetic energy. Our delta kinetic energy is kinetic energy final minus our kinetic energy initial, which is 1/2 mv final squared minus 1/2 mv initial squared. Well, my final velocity is 0. My initial velocity I know. So we have 1/2 our mass, which is 10 kilograms, times 2.5 squared. So we have 1/2 times 10 times 2.5 squared. This will give us the initial, changing kinetic energy, which is what, Brandon?
31.25.
31.25. What's our units?
Joules.
We good with that? Yes, no, maybe so? What are we missing with it? We're missing something. Negative. Negative. The object is moving at 2.5 meters per second initially. It's moving, so it has kinetic energy. Then it goes down to 0. So it has lost our kinetic energy. How much kinetic energy did we lose? 31.25 joules. So we have to throw a negative with that. Well, this change in kinetic energy is also our net work. Our net work is also calculated by our force net. Times displacement. Well, that displacement gives us that distance there that we're looking for. We know the work net, but we don't know the force net. We don't know a net force here. Well, how do I find my net force? Well, I had to sum up all the forces in a direction. Is the sum of our forces in a direction. In this direction, we're only just going horizontal here. We have no vertical motion. We have no trajectory motion. We're not at a slant. We apply a force, we give it a kick, and give it a velocity of 2.5 meters per second. But once we gave it a kick, we didn't have any prolonged contact or any other contact with this object. So there's no force being applied to it here. It was a force applied to get it started to go to 2.5 meters per second, but there's no other forces. We didn't keep pushing behind it. We didn't keep kicking it as it kept on going along. We just kicked it once and got it going at 2.5 meters per second. So the only force that's going to be working here is your force of friction. Well, how do I calculate my force of friction? Because you have no force applied, so we just have a negative or a force of friction. That is the only force. This is the only force in action here, the force of friction. Unless you have wind blowing behind it, or like I said, if you had a dog pulling it along, then you'd have another force being applied. But our initial kick is just me pushing something. I give it an initial velocity, then I let go. Eventually, it's going to slow down. So go ahead and find your force of friction. How do I find my force of friction? Oh, we start pulling everything out now. That's mu times force normal. Well, how do I calculate my normal force? Well, I have a 10 kilogram mass with this sled. How do I find its normal force? Calculate your force of friction. Force of friction comes down to what, Bennett? 9.81. Since it is going against motion, it's going back in this direction. So what should we throw with that? Negative. So our force net is equal to negative 9.81 newtons. That's the only force that's being acted here. Once again, there's no other forces that continue to push this thing along. So our force net, our work net, is equal to negative 31.25 joules. This is equal to our net force, negative 9.81 newtons, times the displacement. So we can divide by the negative 9.81 and find how long or how far does it take for it to stop. How far does it take, Katie? 3.19 meters. Divide by our negative 9.81 newtons. Newtons, a joule is a newton meter. So the newtons will cancel out, the figs cancel out, and just leaves us with the meters then. A 2,100 kilogram car starts at rest at the top of a driveway that is sloped at an angle of 20 degrees with the horizontal. Average force of friction force is 4,000 newtons, impedes the car's motion so that the car's speed is 3.81 meters per second at the bottom of the driveway. What is the length of the driveway? Well, hopefully, what we just did is going to assist us a little bit now. But what we have here is we have an inclined plane. So doing our setup that we did with an inclined plane. We have a 2,100 kilogram car. We have an average force of friction, so we don't have to calculate this, 4,000 newtons. We have a speed at the bottom of the driveway, down here at the bottom, of 3.8 meters per second. And we want to find this displacement, how long the driveway is. Well, the car starts at rest at the top of the hill. What's our velocity at the top of the hill, Anna? 0. So we have an initial velocity of 0. We have gravity doing work here. So we have our force parallel and our force perpendicular. Well, our force, normal force, or our perpendicular force always went into our coefficient of friction. Well, we're given the force of friction already. So we really don't have to deal with force perpendicular. You can calculate it if you want. Go ahead and calculate your parallel force and our perpendicular force. We have the mass of the car is 2,100. So my mass, what's my force of gravity? What's the weight of the object? Once you find the weight of the object, then find your force parallel, force perpendicular. Check your answers with somebody around you to make sure you're going in the right direction here. Should have a force of gravity of 20,601 newtons. Taking 9.81 times the 2100. Our force parallel, we're going to have to multiply our force of gravity by what, Ozzy? Force parallel? Sine of 20. So we have 20601 sine 20. And then the force perpendicular would be times cosine of 20. Calculate your delta kinetic energy, which is your work net. Determine your change in kinetic energy. Your force parallel should be 7,450 or 7,045.96 newtons. Find your net force, which is the sum of the forces. Your sum of the forces in the direction that we're moving, which is down the inclined plane. I have my parallel force here. I have my force of friction, which is given to us as 4,000 newtons. So what is our net force? And then find your distance. And once again, check your answer with somebody around you. Jordan, what's our change in kinetic energy? 15,062. Did you say 62? Right. That's our change in kinetic energy, which is our net work. Okay, we had to find our force net, which is the sum of the forces in the direction of our motion. That's what we get for our net force. Okay, so we have 70,045.96 minus the 4,000 newtons. So we have our force net, 3,045.96 newtons. That is our net force. So then we can find our distance by dealing with force net times our distance is equal to our work net. So we have force net, which is 15,162 equals 3,045.96 times our displacement. So our total distance down the driveway then comes down to a grand total of what, Dylan? 4.9 meters? Yes, no, maybe so? Was that close? Once again, don't worry about if we lost a penny or two somewhere along the line. Calculate the potential energy and kinetic energy at each point. Calculate the velocity at each point. Okay, we have a roller coaster here. We have to climb the steps to get to the top. We climb the steps to get to the top. Gravity will do all the work for us. We start out with a nice little nudge at the top where the little lever gets lifted and the roller coaster starts to roll. At point A, initially, how do we calculate our potential energy? Our potential energy. How do we calculate our potential energy at that point? Lucas, how do we find that potential energy? Okay, mass times gravity times not displacement, just its height. MGH or MGD, doesn't matter. So we have mass times 9.81 times 100 meters. So we have 981 M joules. Don't know what M is, but we'll see. Doesn't really matter. Do we have any kinetic energy at the top? Have any kinetic energy? No, we don't. It starts rolling, so we have 0 joules there. If we take a look at 50 meters, at the 50-meter mark, we have kinetic energy and we have potential energy. Once again, our potential energy can be calculated by MGH or MGD. So we have M times 9.81 times 50. So we can multiply 50 times 9.81. $490.5 times M. Now the kinetic energy at that point, is going to be 1/2 mv squared. And we don't know any of those values. But what we do know is if this is a frictionless roller coaster, if we have frictionless, this potential energy gets shifted into kinetic energy. So if we take a look, I start out with this number of joules of energy. At this point right here, we have potential energy and kinetic energy. Here we just only have potential energy. Some of this potential energy gets lost, but we gain kinetic energy. So we lose potential energy and gain kinetic. But when we add them up, they should all add up to be the same. So this 981 M joules initially has to equal 1/2 mv squared plus 490.5 M joules there. Now what we can see is this mass can be divided out. We can divide both sides by M by M. So what we're left with is in the equation now, 981 is equal to 1/2 v squared plus 490.5. Which will allow us now to find the velocity. We can add the 490.5 or subtract it to the other side, multiply by 2, and then take the square root. And we get 31.32 meters per second. Does not matter what the mass is. Does not matter what the mass is. Okay, what I want you to do for homework is I want you to finish out the rest of the points. What's the velocity at each one of those points? Okay, at point C, point D, and point E. And that'll be your homework for tonight. We'll come in tomorrow, we'll go over that, and we'll have a few more problems dealing with energies to do.